So, lecture 8, Cat 2 is trigonometric integrals. I tried a new room. So, we need some trig identities from pre-calc. So, one of them that is quite useful is this. Cosine 2x is cosine squared x minus sine squared x. If I write this one as 1 minus sine squared, I will get this. If I write this one as 1 minus cosine squared, I will get this. And if I solve for sine squared, I will get this. If I solve for cosine squared, I will get this. So these are in fact the ones that we will be using a lot. These two identities. Now what is special about these two? As you see, this reduces the exponent. So this is like degree 2 and this is degree 1 in a sense. So this identity reduces the exponent. Now, using those two identities, we can integrate cosine squared x and sine squared x. So cosine squared x is the integral of this thing, and this is 1/2 plus 1/2 cosine 2x. And using the methods that we know, this is 1/2 x, and the other one is 1/4 sine 2x. The same happens here. Now, these two integrals, especially this one, is everywhere, and not everywhere, it's used a lot, so it's good to know this one very well. Okay, now let's move to other examples of trig. Now, another example is this. Well, I will start with a simple one, integral of, say, sine x cosine x dx. Well, as you see, well, this is like u and this is du, right? So if we let u be sine x, then du is cosine x dx. So this integral is in fact integral u du, which is 1/2 u squared plus c. So if I substitute, so this integral is in fact this. Okay? Now we use the fact that this cosine is in fact derivative of sine, or vice versa. Sine is derivative of cosine, in fact minus sine is derivative of cosine. And substitution, we can solve so many integrals involving sine and cosine. Now here is some other examples. Let me erase this. Other examples are like, let's see, integral of, say, cosine to some power t, sorry, dx, what am I saying? So let's say if we have two cases here, when n is even and when n is odd. So let's say n is even. Well, this is in fact the hardest one, I guess, yeah. So this n is even, which means that n is like 2 times k for some k. So this gives me an integral of this sort. Cosine to power 2k x dx, and which I can write it as cosine squared x to power k dx. Okay? Then cosine squared x, I can use this identity here. So I can use that. This is 1/2 1 plus cosine 2x to power k dx. And I continue this way, then I will have cosine 2x to some power k, and then I continue using, well, k might be even or odd again, so I just continue doing the same thing. So this reduces the exponent by k, because this is the exponent k. But I started with exponent 2k. So it reduces the exponent by 1/2. And if you continue this way, in the end you might have cosine 4x, cosine 6x, blah, 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 but all of them have exponent 1. And you can integrate each one of them. So, as I said, this cosine squared, this identity and the other one, they reduce the exponent, or they reduce the difficulty, the level of that, say. So, let's do cosine 4x as an example. I don't want to go any further because then we get into trouble. So, let's see. So, let's just do cosine 4x as an example. So, this I can write it as cosine 2x squared dx. So I use that integral 1/2 plus 1/2. Well, I can write the 1/2 outside, so what should I be doing it inside? So this is 1/2 times 1 plus cosine 2x, and that is squared dx. 1/2 squared is 1/4, so let's, and this one squared is 1 plus 2 cosine 2x plus cosine squared 2x dx. Okay? And again, I'm using an identity which some of you might have forgotten, and that is this identity. Where should I write this thing? A plus b squared is a squared plus 2ab plus b squared. Okay. So I can separate this thing because this only has the degree 2. So I can write it as 1/4 integral 1 plus 2 cosine 2x dx plus, well, let's put a bracket here, and the other one is integral cosine squared 2x dx. Now this one is easier, so, I mean, not easy, but it's manageable. Now this one, again, I use that. So this equals, where should I continue? So let me erase these formulas here and continue over here. Okay, so I have 1/4. Integral of this is x, x, and this one will be 1/2 cosine 2x times 2 plus sine 2x. So that is this part, plus integral inside that is 1/2 times 1 plus cosine 4x dx. Right? Okay, so this is 1/4 x plus sine 2x, and this one is 1/2 x from here plus 1/8 sine 4x, and then constant outside. Okay, so yeah, you can put these two together, so you have 3 halves x, and so that's it. That's how you reduce it. Now, if I had cosine 6, then I had cosine 2 to the power 3, then I had to raise it to power 3, then I would get odd powers. So let's see how we manage odd powers. Now, this was all even powers, except this one, that's power 1. Power 1 is okay. The rest of them is, we should be able to manage them. So let's see. So this was the even power, and the sign is the same, just except you have to use the other formula for sine, and you will get in the end something like that. So let me start here. Now what happens if I have odd power? So odd power is this. So integral, say, cosine n x dx, and n odd means that n can be written as 2k plus 1. It is an even number plus 1. So I have cosine to the power 2k plus 1 x dx. So that is, I can write it this way. Cosine squared x to the power k cosine x dx. Okay? And cosine squared, I can write cosine squared as 1 minus sine squared x to the power k cosine x dx. Right? So now you can see that I have an inside function which is sine x, and its derivative is here. So if I let u be sine x, then du is cosine x dx. So this becomes integral of 1 minus u squared to the power k du. Now I have to raise it to power k. I don't know what k is, but raising it to power k, and you have something in just a polynomial in u. And don't forget to substitute sine x for u in the end. So that is, if I have cosine to power n or sine to power n. Sine to power n is the same, so let me just mention sine to power n in this situation. So if instead I have sine to power n, I simply do the same thing. Sine to power n, then I have sine, and then that is like this, sine squared, sine, and then sine squared, I can write it as 1 minus cosine squared x to power k sine x dx. Now again, I have inside function and the derivative is here, so let u be cosine x, then du is minus sine x dx and dx. So this will becomes integral 1 minus u squared to power k minus du. So it's in fact minus integral 1 minus u squared to power k d. Okay? So, well, as you see, they look like each other, except that in the end you have to substitute cosine for u, and the other one was sine. But anyway, the end result here looks similar, except with this negative sign. Okay, so that is for sine n and cosine n, when n is even or odd. And now if I have some combination of these two, I will do the same. So what is a combination? A combination is something like this. If I have a sine mx cosine nx dx. Okay? have this combination, what should I do? Okay, let's see. If this n is, for example, odd, if this n is odd, well, let's just case 1. If I have case 1, n is odd, so n is 2k plus 1, say, and this gives me integral sine to power mx times cosine squared to power k, again like that, another cosine dx. Now, what is special about this? If you see this, even this is odd, you can write it as an even number plus 1. This plus 1 gives me a single cosine somewhere. So, and I can use this single cosine because this cosine dx is in fact derivative of sine. That's so the cosine is the derivative of sine. So I can use substitution. So let's see. But this is not done yet because I need sine here. So this equals integral sine mx 1 minus sine squared x to power k cosine x dx if I let u be sine x, then this becomes, this gives me du is cosine x dx, and this is integral u to power m 1 minus u squared to power k du. Okay, so that's the case when, say, n is odd. You can guess what happens if m is odd. So, but let me discuss that as case 2. So this is case 1 when n is odd. Now case 2 is when m is odd. So let me erase everything, and case 2 is when m is odd. Now, if both of them are odd, I would choose this one, cosine, because cosine is the derivative of sine, but sine is the derivative of minus cosine, so I would choose cosine. But anyway, so let's assume that the other one, just this one, let's just, if this one is odd, let's take this one. So if m is odd, then m equals something like 2k plus 1, and then I will get this instead of this. So I have sine squared x to power k, and I have cosine to power nx, but I have one sine left, sine x dx, right? It comes from this 1 here. So this is 2k plus 1. Then I write it like this, so I have, I write this one as 1 minus cosine squared x to power k cosine nx sine x dx. So if let u be cosine x in this case, then du is minus sine x dx, right? So this becomes integral 1 minus u squared to power k u to power n minus du, right, times minus du, and I can write this minus outside, minus. So this looks like the other one, but I use the sine in this case. Okay, so if one of them is odd, the problem reduces to finding, it reduces to integral of a polynomial in this u. I know you have to raise this to power k. There's no way. You can only do it by raising it to power k, and you have a long polynomial. If k is large, then you have to integrate that. Now, what happens if both of them are even? So that's case 3. And that's the most difficult one. Remember the even. So case 3 is